Okay, now today let us start the part 2 of chemical reaction engineering, which directly focuses on the kinetics of reactions. Uh, Most importantly, this course is given by Natalia is a lecturer and a researcher at Rama University, Rama Institute of Technology, Department of Chemical Engineering. Today let us start with the contents or the lessons of the chemical reaction engineering, which is directly focused on the kinetics of the homogeneous reactions. So today let us see definition of chemical kinetics, classifications of chemical reactions, what are the classifications of chemical reactions, on what basis the chemical reactions are classified. Third one is rates of chemical reactions. How we can explain the rates of the chemical reaction with respect to different concentrations. The fourth one is molecularity of reactions. What is molecularity of the reactions? Actually, molecularity of the reactions means the dependent on unimolecular, bimolecular, trimolecular, thermolecular, or trimolecular. And let us see the difference between molecularity and the order of the reactions. What is how we can relate molecularity with the order of the reactions, or how we can differentiate molecularity of the reactions from the order of reactions. So let us see the definitions of chemical kinetics. Mostly the chemical kinetics studies the rate at which the chemical reactions occur or the chemical reactions takes place. For example, A to B. Actually, this means that kinetics means it studies the rate at which A is just converted into B, which means that the reactions or the chemical reactions that occurs while converting the raw materials into the products. And it deals with the factors which affect the rates of the chemical reactions like temperature, pressure, the concentration of the reactants or the compositions of the reaction rates. In addition to this one, the chemical kinetics, it provides an information about the mechanisms of the reactions. What are the mechanisms of the reactions? There is an initiation mechanisms, propagation mechanisms, and termination mechanisms. These are the mechanisms of the reactions. The reactions at which the mechanisms is just developed, reaction mechanisms. The second one is it deals with or it provides an information about or offers a information about the speed of the chemical reactions. The speed at what speed the reactions takes place within the chemical reactors, and it deals with the type of the rate equations depending on the order of the reactions. Actually, either it is first order reaction, second order reaction, third order reaction, or up to n order reactions, or depending on the classifications of the chemical reactions. So in this regard, we will see thermodynamics, which means that actually chemical kinetics deals with the rates of the rate at which the chemical reactions takes place, and it deals also with the effects of different parameters like temperature, pressure, and reactant concentration or composition of the reaction rates. In addition to this one, it deals with the mechanisms of the reaction. In this relation, the thermodynamics, it provides an information about the feasibility of the reaction. Whether the reaction is just feasible or not is studied by thermodynamics, and it also deals with whether the reaction will occur or not under a given set of conditions, or whether the given reaction is just heat absorbed or liberated during the course of the reaction, which means that either it is uh, endothermic reaction or what we call it exothermic reactions. So in design of chemical reactor or in designing of the chemical reactor, we need an information from one thermodynamic, which deals with the feasibility of the reaction, whether the reaction is feasible or not under given circumstances or under a given set of circumstances, which means that the heat is just absorbed or liberated during the course of the reaction, as well as it deals with the chemical kinetics. The chemical kinetics means providing an information concerning with the reaction mechanisms the speed of the chemical reactions, and the type of the rate equation. The rate equation which is dependent, which is directly with first order, the rate equation directly with second order, the rate equation with third order, or the rate equation with nth order of the reactions, or in other words, the rate equations which is directly dependent on the what we call the classification of the chemical reactions. Classification of chemical reactions. The second one is classification of chemical reactions. Classification of the chemical reactions. Actually means classification of the chemical reactions means within a given reactor, different reactions are takes place. Different reactions are takes place. Either uh, those reactions are in regard with reactor, in regard with a given reactor, or in regard with a vessel. So the chemical reactions may be classified depending on the number of phases involved as one homogeneous reactions, the second one is heterogeneous reactions. Depending on the number of the phases. Number of phases means normally either it is a liquid phase, solid phase, or gaseous phase. That is considered as uh, phases which are involved. It can be classified as homogeneous and heterogeneous reactions. So, homogeneous reaction is the type of reaction which takes place only in one phase. Only in one phase. Which means that all the reacting material, for example, if A plus B gives us C, what does it mean? That all the reacting materials, the products as well as the catalysts which are just utilized for the conversion of the reactants into products exist only in a single phase. Exist in only a single phase. Actually, in this case, in A plus B gives us C. A and B are the reactants or the reacting materials. C is the products, and let us take nickel as a catalyst. So nickel is considered as a catalyst. Those all the reacting materials, the product, and the catalyst are exists in a single phase or in one phase. This is considered as a homogeneous reactions. Let us see an example of homogeneous reactions. For example, the oxidation of nitrogen oxide to nitrogen dioxide with air is a gas phase reactions. Actually, NO plus 1 over 2 oxygen, it gives us NO2, nitrogen dioxide. These reactions are considered as a gas phase reaction. A gas phase reaction, normally the phase of this reaction is gas. Normally this reaction exists only in one phase. The reactants, which means that NO, nitrogen dioxide or monoxide, and oxygen are the reacting material, and the product, nitrogen oxide, with the help of air, you can consider air as a catalyst. Those all materials are existed in one phase. This is considered as a gas phase reactions. The second one is formation of esters from organic acids and alcohols in presence of sulfuric acid is a liquid phase reactions. So alcohol, which means that C2H5OO OH plus acetic acid, which means that acetic acid is a type of organic acid, CH3COOH gives us what we ethyl acetate, which means that ester. Ethyl acetate is a type of ester, which is CH3COO C2H5 plus water with the help of the catalyst known as sulfuric acid. So in this case, sulfuric acid, the reacting materials means ethanol, or what we call it, ethanol is normally a type of alcohol. The other one is acetic acid. It is a type of organic acid. Acetic acid with the help of sulfuric acid. Sulfuric acid is considered as a catalyst. It is considered as a catalyst. Then it forms ester, which is ester. In this case, the type of ester is ethyl acetate. ethyl acetate plus water. Those materials, the products, the catalysts, and as well as the reactants are, or the reacting material exists in a liquid phase reaction. So, oxidation of nitrogen oxide to nitrogen dioxide with the help of air as a catalyst is, and formation of esters from organic acids and alcohols in the presence of sulfuric acid is a good example of homogeneous reactions. Good example of homogeneous reactions with the first one, oxidation of nitrogen oxide to nitrogen dioxide with the help of air exists in gas phase reaction, and the formation of esters from organic acid, normally reaction of alcohols or ethanol plus acetic acid or organic acids, which gives us ethyl acetate, which is ester plus water with the help of sulfuric acid, exists in liquid phase reactions. Those reactions are a good example for homogeneous reactions which exists only in one phase. Either it is a gas phase reaction or what we call it a liquid phase reactions. The second one is heterogeneous reactions. Heterogeneous reaction is a type of reaction in which the reactions exists or occur in more than one phase. In more than one phase, which means that at least one of the reactants, the catalyst and the product is present in a phase which is different from that of the remaining components of the reacting system. For example, oxidation of sulfur dioxide to sulfur trioxide, or which means that reacting sulfur dioxide plus half of oxygen, which gives us what we call sulfur trioxide with the help of the catalyst vanadium pentoxide. Vanadium pentoxide. So from this we can understand that sulfur dioxide, oxygen as well as SO3 is considered as a gaseous phase reaction. Vanadium pentoxide, which means that the catalyst is a solid material. So those materials, the catalyst as well as the reacting materials are in different phases, not occur in a single phase. It's a single phase. Reacting materials as well as the products are in gaseous phase. The catalysts are in, which means that it is in a solid phase. It is considered as a solid material. So this is a good example of heterogeneous reactions. Second one is the reactions may be classified as catalytic and non-catalytic reactions. Catalytic reactions are reactions that involve the utilization of catalysts to enhance or to speed up the rate of the reactions, to enhance or to improve the rate of the reactions, which means that catalytic reactions are in case of activation energy, the catalytic reactions have low activation energy and non-catalytic reactions have high activation energy, which means that in order to convert the reactants into the products, the conversion takes place within a short period of time, within a short period. It didn't take more time, it didn't consume more time since it is a catalytic reaction. That's why the utilization of energy or utilization of the activation energy, which means that the activation energy that is required to transform the reactant into product with the help of catalyst is very low. Examples of catalytic reactions are hydrogenation of ethylene, what we call it C2H4 plus hydrogen, which gives us C2H6 with the help of nickel catalyst. With the help of nickel catalyst is a type of catalytic reactions. Catalytic reactions because normally the catalyst didn't involve in the reaction, but the purpose of catalyst is to speed up the rate of the reaction. The second one is non-catalytic reactions, which is the reactions which does not involve the use of the catalyst. For example, if you take oxidation of nitrogen monoxide into nitrogen dioxide, this is a non-catalytic reactions. In non-catalytic reactions, the activation energies which is utilized for conversion of reactant into product is very high as compared with catalytic reactions. These are the types of reactions based on the what we call it speed or based on the rate of the reaction. The other one is The reactions may be classified based on the molecularity of the reactions. Based on the molecularity of the reactions. Molecularity of the reaction means based upon the number of molecules which is participated in the reaction, or what we call it in rate determining step, as a unimolecular reaction, a biomolecular reaction, a thermomolecular reaction. For instance, the composition of cyclobutane is a unimolecular reaction. For example, a cyclobutane reaction is H2C single bond CH2 from hydrogen, H2C from this one, H2C, then what we call CH2, then it decomposed into what we call decomposed into ethylene, 2C2H4. So this is a unimolecular reaction, a unimolecular. For example, the composition of hydrogen iodide, which means that 2Hi gaseous phase reaction, which gives us what we call it iodine gas plus hydrogen gas. This is considered as 2 because here uh, the what we call is the coefficient of hydrogen iodide is 2, so it is considered as a biomolecular reactions, which means that due to the decomposition is takes place due to the collision of two molecules, for instance, oxidation of NO, what we call it 2NO plus oxygen, it gives us 2NO2. So 2 here, 1 here. The coefficient of nitrogen monoxide is 2, the coefficient of oxygen is 1. We can consider it as a trimolecular or thermomolecular reaction which involves the collision of 3 molecules, which means that 2 is from nitrogen monoxide, 1 is from oxygen. It gives us a trimolecular reaction. So let us see. Normally this means 2NO plus oxygen, which gives us what we call it 2NO2. So 2 moles of nitrogen monoxide collides with 1 moles of oxygen. This means that the collision of the materials, or what we call it 3 molecules are colliding, 2 from nitrogen monoxide, 1 from oxygen. This is considered as a classification of the reaction based on the molecularity. The other one is the reactions may be classified based on the effects of it according as they give off or absorb heat to or from the surrounding, as exothermic reactions and endothermic reactions. Exothermic reaction means is one in which heat is just evolved. What does it mean? That it is enough of energy, high supplies of high, it contains high energy, so it can release heat to the environment. For example, the reaction between CO and hydrogen to produce methanol is an exothermic reaction. This is an exothermic reaction. The other one, endothermic reaction, is the one in which heat is absorbed. Heat will be supplied to the reacting system from the surrounding for a reaction to take place. So without exothermic reaction, there is no endothermic reaction. So there is what? A supply. Exothermic reaction releases or gives heat to endothermic reaction. Endothermic reaction takes energy from what we call it exothermic reaction. For example, dehydration of ethyl alcohol to produce ethylene is an endothermic reaction. So endothermic reaction means it has a negative energy. Exothermic reaction means it has a positive energy. It is considered as a positive energy, in other words. The other one is the reactions may be classified based upon the order of reactions as a first order reaction, a second order reaction, a third order reaction. A reaction of which overall order of reaction is 1, which means the sum of the orders with respect to the participants in reaction is unity, is called as a first order reactions, which means that the number of exponent is just equal to 1. The number of exponents, for example, A gives us B, which means that the rate of reaction for A is equals to KCA the power of 1. So in this case, N is equals to 1. This is considered as, when the exponents are 1, this is considered as the first order reaction. Second one is a reaction of which the sum of the orders with respect to the reactants participating in reaction is 2 is called what we call it a second order reactions. In other words, the rate of the reactions with the sum of the orders with respect to reactant is 3 is considered as third order reactions. The same is true, the rate of the reaction or a reaction of which the sum of the order with respect to reactant to participate in reaction is n is considered as nth order reactions. In other words, the reactions are also classified as reversible and irreversible based upon whether they proceed in one or in both the directions. So reversible reactions are those in which the forward reaction as well as the reverse reactions takes place simultaneously. There is a simultaneous occurrence of the forward as well as the backward. For example, if you see the conversion of A to B and there is a conversion of B to A. This is considered as a reversible reactions. The other one is irreversible reactions are those in which proceed only in one direction. For example, from A to B or what we call it from B to A. This is considered as an irreversible reaction. Reactions either in what we call it in forward or in reverse directions. This is considered as an irreversible reactions. Now let us proceed into the rates of the chemical reactions. So how we can explain or how we can write the rates of the reaction with respect to different reactants. The rate of a chemical reaction may vary from a large value, which means that instantaneous reactions, to essentially zero, which means that there is a zero order reaction, there is a second order, there is a fraction order reactions. In ionic reactions, such as those that occur in photographic film or in high temperature combustion reactions, the rate is extremely fast. The rate of combination of hydrogen and oxygen in the absence of catalyst at room temperature is immeasurably slow, which means that the conversion of hydrogen with oxygen into some product is just with the help of catalyst is just well, but with the help of non-catalyst is normally immeasurably very low. Most industrially important reactions occur at rates between these extremes, which means this extreme means there is a slow reaction, which means that's the rate determining step, and the second one is extremely fast rate of reaction. The rate of reaction can be defined in a number of ways. Normally, we can define the rate of reaction in a number of ways for homogeneous reactions. Since this chapter is directly, or this part of the lesson is directly focuses on what we call it in homogeneous reactions systems, we can explain the rate of reactions based on what we call it a unit mass of the solid or a unit volume of the reacting fluid, as well as for fluid solid systems for what we call it for heterogeneous reactions we can explain based on unit mass of solid in case of fluid solid systems or what we call it as solid catalyzed reactions. The second one is here we can explain, let us focus it or later write it, the rate of the reactions. So here we express the rate of the disappearance of component A if the rate of change in a number of moles of reactant A is normally there is a change rate which is equals to there is a change minus, since the reactant is the reaction, we can consider it as the change in Na divided by the change in T. So if the rate change in a number of moles of reactant A is minus dNA by dt, moles of A with T, then the rate in its various form is defined as follows on different bases. So based on unit volume of the reacting fluid, we can explain the rate of the reaction minus rate of A. This minus indicates that the reactants are just consumed in the reaction, or there is a disappearance of the component A. Since the reactant is just converted into the product, we can say that the graph of the rate of the reaction with respect to the concentration is just decreasing. The reaction is just since the reactant is just converted into the product, or the reactant is consumed in the reactions. So the rate of the reaction is explained as minus 1 over V dNA by dt, where this is Na, which means that the moles of the A disappeared, divided by volume of the fluid times time. This is normally for what we call it homogeneous reactions. This one is for homogeneous systems or homogeneous systems. But for a fluid solid systems based on a unit mass, we can explain the rate of the reaction as the rate of the reaction minus Ra minus, which is equals to minus 1 over W. This is just a fluid solid system, means normally for a solid catalyzed reactions, or what we call it for a fluid solid systems, dNA by dt. This indicates that change in Na is moles of A disappear, W is mass of the solid, T is normally the time. Normally change in N A divided by change in T, the gradient of moles of A with respect to time. The other one is based on the unit interfacial surface, or in fluid systems, or based on the what we call it a unit surface of solid in a gas systems. So minus Ra plus dot dot, which is equals to 1 minus of 1 over S dNA by dt. This minus indicates that consumption of the reactant, consumption of reactant indicates the consumption of the reactants. Based on unit volume of the solid in a gas solid systems, you can explain as minus Ra 3 dot is equals to minus 1 over Vs dNA by dt. Moles of A disappear over volume of the solid times time. So in this case, Vs is directly equal with Vp. Since it is a solid catalyzed reactions, Vp is normally volume of the catalyst pellets. Normally volume of the catalyst pellets is just for either for it is cylinder or a spherical catalyst. We can just explain it in the form of what we call it for a spherical catalyst as well as for cylindrical catalysts. So based on a unit volume of the reactor, we can explain as minus Ra dot dot 3 for minus 1 over Vr dN by dt, which means that moles of A disappear divided by volume of the reactor times time. So since we are considering a homogeneous systems or homogeneous reactions, V and Vr are identical, which means that volume of the fluid in the reactor is identical with volume of the reactor. So in this case, we can write it as the reaction rate is an intensive property or quantity, and it depends on the concentration as well as time. The above rates are related by, which means that since Vr is directly equal with V, we can write it as in such form, because dNA by dt, which is equal to minus of Ra times V, is equals to minus of Ra times W for what we call it for a fluid solid catalyzed reaction, is equals to minus of Ra prime prime S is equals to minus Ra prime prime Vs is equals to minus of Ra for Vr. These are when the change in Na with respect to what you call it T is just since it is constant, we can write it as like this one. So in homogeneous systems, the rate of the reaction is defined based on the unit volume of the reacting fluid. The reacting fluid, which means that Ra, which is equals to 1 over Vr dNA by dt, or we can write it as Ra, which is equals to minus d by dt, then Na divided by volume. So for homogeneous systems, the rate of reaction is defined as the change in moles of the reactant or a product due to the reaction per unit time per unit volume of the reacting fluid or the reaction mixture. Mathematically, this can be written as if A is just converting into P, or what we call it B, the rate of the reaction can be written as rate of reaction is equals to minus 1 over Vr dNA by dt. So in other cases, the rate of the reaction may be expressed either as the rate of the disappearance of a certain reactant or the rate of the formation of a certain product. The rate of reaction normally is a function of the rate of the formation of the product, the rate of the formation of a product, or the rate of the disappearance of the reactant, or what we call the consumption of the reactant in a reaction. It is a positive quantity and tells us how the concentration of the reactant or product changes with time during the course of the reaction, which means that the rate of the reaction is directly equal to minus of 1 over Vr dN by dt, which means that the rate of the reactant or the rate of the product is just altered during the course of the reactions, or what we call it, the reactant is just converting into the product. During this, the reactant is just consumed in the reaction. This is considered as the rate of the reactions. So let us consider an irreversible reaction. An irreversible reaction means it is a one-way reaction. Either this one is a forward reaction. This is considered as forward reaction. Forward reaction. Forward reaction, which means that A, capital A plus B, small b, capital B gives us R small, R capital. So this reaction is normally, it is considered as an irreversible reaction in which A and B are the reacting component. A capital and B are the reacting component. Small a, B and R are the coefficients of the for A and B, for reactant A and B, R for product. As per the above reaction, A and B are disappearing due to A and B are just consumed in the reaction. There is a consumption in the reaction. There is a transformation of the reactant goes A and B to R, and R is being produced, which means that it's considered as a formation. R is formed as a result of the reaction of A and B. Therefore, A and B considered as the reactant, R is the product. So the rate of the reaction with respect to A, rate of disappearance of reactant A, is written as minus Ra, which is equals to minus 1 over B, volume of the fluid, dNA by dt, which means that amount of moles of A disappearing or amount of moles of A consumed in the reaction divided by volume of the fluid times time with the unit mole divided by what we call it liter second, because the unit of the mole is considered as mole, number of moles, mole, the volume is normally it is liter, time is given in what we call it second. So we can write it as the rate of the reaction with respect to the above reversible reactions. Second one, where Na is the moles of the component A. For the constant volume of the reaction mechanisms, normally if the volume of the reaction system is constant, we can write it as the moles of the reaction as minus D in bracket Na divided by V divided by dt. But mole divided by volume is normally it is a concentration. So the rate of the reaction Ra, which is equals to minus dCA by dt, which means that the concentration of the reactant is just consumed in the reaction. Therefore, for such systems, the rate of the chemical reaction may be expressed as the rate of the change of concentration of any reactant or the product of the chemical reaction. So for B also we can write as minus 1 over V dNA by dt, which means that which is directly equal to NB, N for reactant B divided by V, D by dt, which is minus RA, which is minus. So minus RA, which is equals to Na by V, which means that concentration of B. So dCB divided by dt. Or we can write as the rate of reaction as R, because the minus the rate of reaction for A and the B are, we can write the rate as minus for the reactant, but if it is for the product we can write it as positive, because the graph of concentration with respect to reactant is what we call it increasing, an increasing graph. So that's why the rate of R, which is equals to minus not minus dc r by dt, normally for the product as well as for the reactant. So from the above, the negative sign in case of reactant and the B indicates that concentration of reactant is decreasing with time. Normally concentration with respect to time is just for the reactant increasing, for the product is just for the reactant decreasing, for the reactant it is just increasing. So the relation between the rates of participants in a chemical reaction from the stoichiometry of a reaction is written as the rate of the reaction for A divided by A minus rate of for B divided by what we call it B, which is equals to R, the rate for R divided by smaller. So the stoichiometry of reaction for the reaction A plus 3B, which gives us 2R. How we can write? Rate of A divided by 1, rate of B divided by 3, rate of R divided by 2. From this we can understand that the rate of the disappearance of P is 3 times the rate of the disappearance of A. So rate of disappearance of B, which is equals to 3 times the rate of disappearance of A, or the rate of formation of R is twice the rate of disappearance of A. This is how we can just generalize depending on the stoichiometry of the reaction. In this relation, or in this regard, there are factors that affect the rate of the reaction. So the rate of the reaction from the above statements or from the above explanations, we can understand that the rate of the reaction is just affected by several factors, like the nature of the reactants and the products, the pressure of the system, temperature of the system, temperature of the system, the surface area of the reactants, the rates of the mass, as well as what we call it heat transfer, as well as the nature of the catalyst if it is present. The nature of the catalyst or the characteristics of the catalyst affects the rates of the reaction or the rates of the chemical reactions. So for homogeneous systems, the possible factors that affect the rate of the reaction are what we call temperature, pressure, and the composition, what we call is the concentration of the reactant. Normally for homogeneous systems, so we will consider the reaction, which means that the rate of the reaction in relation with temperature, pressure, as well as the composition. These are interdependent factors, and the pressure is determined given the temperature and the composition of a phase. Hence, for homogeneous systems, we can write the rate of reaction as a function of temperature and the composition, which means that the rate of the reaction normally homogeneous, it is written as in the function of temperature dependent terms and the concentration dependent terms. So as an example, let us see. For example, A gives us R, a single reactant into a single product. From this we can understand that the rate of the reaction with respect to what we call it, what if it is affected by what you call it temperature. Ra, which is equals to K Ca the power of alpha, which means that K from Arrhenius equation we can relate to is K naught, which means that the pre-exponential factor E the power of activation energy divided by R times T. This indicates that how the rate of the reaction is affected by the temperature of the system. So minus R is equals to K times Ca the power of alpha. Alpha is normally, it indicates the order of the reaction with respect to A. So K, which is equals to K naught, is the power of minus E over RT. So it is dependent on what you call the temperature of the system times concentration of A. This shows that the rate of the reaction is just dependent on the temperature of the system as well as the concentration of the reactants. That's why the rate of the reaction is affected mostly for homogeneous system is affected by the pressure of the system, the temperature of the system, as well as the concentration of the reactants. Let us proceed into molecularity of the reaction. Many chemical reactions proceed through a number of steps. A number of steps. A number of steps means there is an initiation step, there is a propagation step, there is what you call it the termination steps in reaction mechanisms. Each of the individual steps is called as an elementary step. But the full consideration, which means that initiation step, termination step, or what we call initiation step, propagation step, then termination step. So initiation, there is intermediate reactions, then last is termination one. If you consider this one, this is considered as non-elementary reaction or non-elementary step. The rate of reaction is determined by the slowest step. The slowest in rate of reaction, the slowest step is the rate determining step. Hence, it is known as the rate determining step. So what is molecularity of the reaction? It means molecularity is the number of reacting species. For example, there is a molecules, atoms or ions which collide simultaneously to bring about a chemical reaction in an elementary reaction in the rate limiting or a rate determining step of the reaction. For example, if you consider A plus B gives us R. So what is the molecularity of this reaction? The molecularity of this reaction is a bimolecular because one molecules of A is just reacting with one molecules of B, or one atoms of A is reacting with one atoms of B. This is considered as the collision of two molecules. The collision of two molecules, which means that the collision of two molecules, one from A, B, one from B, in order to bring the chemical reaction. So in this case, we can determine what we call the rate limiting or the rate determining step, or the rate is just low in that case, the slowest step of the reaction. If one molecule is transferred in an elementary process, the reaction is called a unimolecular. Normally, unimolecular means if one mole of the substance or molecule is just transferred, we can consider it a unimolecular. If it is two, bimolecular. If it is three, trimolecular. It may be noted that reactions with a molecularity of 3 or more are uncommon. It is not common. This is due to the fact that such reactions require the simultaneous collision of 3 or more molecules. It requires what we call 3 or more molecules. It requires 3 or more molecules, and which is rare. In case of complex reactions, the overall chemical reaction does not provide any clue to the number of molecules colliding except in a single reaction. Hence, molecularity has no meaning for overall reactions. Normally, it works for only a simple reactions, only for a simple reaction, not work for what we call it for a complex reactions. It is concerned with each elementary step or reaction which proceeds through one step only. Molecularity of reaction must be a whole number. It never be zero or fractions. Since because of what we call it, molecularity of the reaction is a theoretical quantity. Theoretical quantity. It is considered as a theoretical quantity because A gives us A plus B gives us R, which means that the collision of two molecules, one molecule from A, one molecule from B. This is considered as what we call as the molecularity of the reactions. Let us proceed because since uh, since the term order of reaction and what we call molecularity of reaction is confused, it makes confusion. Since it makes a confusion, let us proceed into order of reactions. Order of a reaction is defined as the sum of the exponents of the concentration terms in rate expression or in a rate law. For example, A plus B, which gives us C. From this we can understand the rate of the reaction. You can write as K times the concentration of A, the power of 1. The power of 1. This 1 or the power of n. This n is the order of the reaction. The exponent, based upon the assumption that only molecules which collide can react. The rate of the reaction is proportional to the number of collisions. At a given temperature, the number of collisions is directly proportional to the number of molecules. Hence, the rate of a chemical reaction should be proportional to the concentration of the reactants. Hence, for the reaction of the type, which means that small a, the coefficient, capital A plus small b, capital B, plus the continuous goes into R, capital R plus S, capital S. So from this one, the rate of the disappearance of reactant A is given by minus reactant A, which is equals to minus dCA by dt, which is equals to K concentration of A, the power of N1 times concentration of B, the power of N2, where N1 and N2 is the order of the reaction. Overall, you can write it as N1 plus N2. This is considered as the overall order of the reaction. Minus RA is the rate of the reaction with respect to reactant A. We can explain with respect to reactant A or with respect to the reactant B. So the mathematical expression giving the functional relation between the rates of the reaction and the concentration of reactant is considered as the rate law or the rate equation, or the simply we can say rate, or we can say the kinetic expression, the rate kinetic expression. So the order of the reaction or the overall order of the reaction from the above reaction is N, which is equals to N1 plus N2. It continues. If the order of reaction continues, we can use it. So the order of the reaction with respect to a particular reactant is the exponent of the concentration of the reactant in the rate equation A plus B, which gives us R, which means that A and B are colliding in order to form what we call it R. So the rate of the reaction is just written like this one. The same is true for the decomposition of hydrogen peroxide into water and oxygen. The rate with respect to reactant hydrogen peroxide, which is equals to minus this one, which is equals to K concentration of this one, the power of 1. So N overall order of the reaction is 1, or what we call the first order of the reactions. Now let us see the difference between molecularity and the order of the reaction, because the term molecularity and order in chemical reaction is just, it confuses, it makes a confusion. So the molecularity is defined as simply a number of molecules, atoms or ions which participates in a chemical reactions, and which limits the rate or which determines the rates. So the order of the reaction is simply, it is the sum of the exponents of the concentration terms in the rate law equation. Normally, A plus A gives us R. A is just participated in the reaction, but the concentration, which is the concentration term, which is the power 1 or 2 or n, is considered as the order of the reactions. A, which gives us R, which means that the molecules which participate in the reaction is only A. So the coefficient is 1. So we can consider it as this one is molecularity or a unimolecular reactions. The other one is molecularity of a reaction is a theoretical quantity to satisfy the experimental findings, whereas the order of the reaction is entirely an experimental quantity. Simply molecularity is theoretically you can just say it, or theoretically we can identify it, or you can quantify it. But order of the reaction is just determined through experiments. It is an experimental quantity, an experimentally determined quantity. Molecularity of a reaction must be a whole number and it will never be zero or a fraction. But the order of the reaction is whole number, zero, or it is fraction. It is possible. It's possible. So thank you for today's lesson. Normally as a reference book you can use Chemical Reaction Engineering textbook by Octave as well as textbook of Chemical Reaction Engineering by Fogler, or what we call it a Chemical Reaction Engineering written by Govani in addition. So thank you for your attention.